When we think about the size of things, we tend to think of the size of things with reference to ourselves. So, the foot or the meter, or those things, or the inch or the centimeter, what are those things? Ultimately, historically, they're based on properties of the human body. So they're based on biology. And that's what we did historically, because why would you do anything else? Is that fundamental? Well, the answer is no. It doesn't tell you anything profound or deep about the deep structure of the universe. But of course, the history of physics tells us, as we go into the 17th century, the 18th century, the 19th century, 20th century, we then begin to understand that there are things that are much bigger than us and much smaller than us. We're looking, I suppose, for units of measurement that you could imagine if we met some aliens from some different civilization. They might not even have arms, right, or feet, but they might be very different in size and scale from us. So what would the common language be? Is there some unit of measurement that we could all agree on? I'm Brian Cox. My full title is Professor of Particle Physics at the University of Manchester, Royal Society Professor for Public Engagement in Science and Visiting Scholar at the Crick Institute. Or you could just call me Brian. What are the fundamental quantities, as far as we can tell, that really tell us something about the structure of nature? So one will be the speed of light. Everything that is massless travels at the speed of light, at this speed, whatever it is. If you have any mass at all, you cannot travel, you cannot accelerate to this speed. Another one will be the strength of the gravitational force. So what is the force between two objects of a particular mass? Or in Einstein's theory, how does a particular amount of matter or energy distort the fabric of the universe? The number that tells you about that is Newton's gravitational constant, which was first measured back in the 1780s, 1790s. And then there's Planck's constant itself. In 1900, Max Planck made a revolutionary proposal. You could say, for example, that there's a fundamental limit on how accurately we can know the position of a particle and the momentum of a particle. You can't know them both with absolute precision. There's a fundamental limit, and it's around about Planck's constant. Planck first introduced it in the context of the frequency